this. Coding efficiency is 50%, right? So we are going to discuss the 6-3 linear code today, and because the value of n and k in the case of 6-3 does not satisfy the criteria, the formula for the Hamming code, so it's not a Hamming code. Okay, so the first definition we have seen today is linear code, and we have already seen a type of the linear code, which is the Hamming codes. So the Hamming codes are linear codes, and today we are going to see another type of linear code called as the 6-3 code. And what do we mean by linear code? The sum of any two code words produces another code word. Now, to produce this 6-3 linear code, we need to create the generator matrix. So because it's 6-3, that means it has 3 information bits and 3 parity bits. So the total block length is 6. So with 3 information bits, we have how many different messages? We have 8 possible messages. Hello? Is my sound gone for everyone? Or only one person has lost my sound? Hello? You can hear me, right? Yes, okay, mashallah, very good. Okay. I think it was only one student. So whichever student he was not able to hear me, please log out and log in. Abdullah Muhammad ibn Murray, you have to log out and log in. Let me reply to him. Excuse me, guys, let me reply to him because he can't hear me. Log out and log in again. Okay. Right, guys. So we will see how to make the generator matrix for the 6-3 linear code. And since the value of k is 3 and the block length is 6, that means we have 3 information bits and we are going to add 3 parity bits. So it makes it a code block length of 6 bits. So that means we have information bits which are 0, 0, 0, 0, 0, 1 up to 1, 1, 1. So there are 8 possible combinations, 8 messages, right? So each of these messages we are going to convert into a code word. So 0, 0, 0, we'll add 3 parity bits and make it as a code word of length 6. So 0, 0, 1, and we'll add 3 code words, 3 parity bits. Similarly 1, 1, 1. All the 8 messages will be added with the corresponding parity bits. So the 8 messages will be converted into 8 code words. Right? So we will have 8 different code words that will be produced. Now, how to produce these code words? To produce the code words, we will need to have a generator matrix. And because we are going to have this again as a systematic code, the first part of the generator matrix will be an identity matrix of size k by k. So since k is equal to 3 here, the value of k is 3. So k by k matrix means a 3 by 3 identity matrix will be the first half of the generator matrix. Then the second half of the generator matrix will be the 3 columns which is going to produce the 3 parity bits. Okay, so let's do that. I'm going to erase the board and I will have to write it from scratch. So I'm going to clear the board. If you want to take a screenshot of the board, you can take it now. What is written on the board before I erase it? All of you, if you want to take a screenshot of what is written, take a screenshot quickly. I'm going to erase it in 10 seconds. All right, here we go. I'm going to erase it. Okay. Right. So the generator matrix, we are interested in making the generator matrix. I will upload this right. Well, I'm recording this video. If it gets recorded, I will upload it. I don't know this Blackboard Ultra. Sometimes it records the video. Sometimes I don't know where it disappears. Hopefully it is getting recorded. If it is recorded, I will inshallah upload it. Okay, we want to make the generator matrix. Why don't I use Zoom? Well, I don't know. I started with the Ultra. I've been using Ultra. We could use Zoom also, but let us stick to this now. Generator matrix for 6, 3 code. Okay. This is what we are going to do now. So we want to make the generator matrix G, and because it is 6, 3, the first part of the generator matrix will be a 3 by 3 identity matrix because the value of k is 3. So we are going to have a 3 by 3 identity matrix. So 1, 0, 0, 0, 1, 0, and 0, 0, 1. So that's an identity matrix of size 3. And then the second part of the generator matrix is the parity matrix of size n minus k. In this case, n minus k is 6 minus 3. So which is P of size 3. That means it has 3 columns. So the 3 columns of the generator matrix, of the parity matrix, will have to be created according to a specific way, and that is going to be by following the rules that we discussed in the last lecture. First of all, it should not be all zeros. None of the rows of the P matrix should be all zeros. It should not be repeated, and it should have at least 2 ones in it. So with that condition, we can choose them as 1, 1, 0, 0, 1, 1, and 1, 0, 1. So that is now our generator matrix. And how do you produce the code word? You will multiply all the 8 messages with the generator matrix like we did for the 7-4 Hamming code, and you will get the code words. So I'm not going to do that calculations. You can do the calculation of the code words by yourself, I suppose. So that will not be necessary for me to do it again, isn't it? Or do you want me to do one example? Let me do just for the benefit of some students. So let's say if we have a message 101, okay, and if we multiply this with the generator matrix 101 with this generator matrix, what do we get? The first 3 bits will be the same because it is systematic. We have an identity matrix in front, so the first 3 bits will be the same, 101, and then now you will multiply these elements bit by bit with each of the columns of the P matrix. That will give you the parity bits. So 1 into 1 is 1, 0 into 0 is 0, 1 into 1 is 1. So it's 1 plus 1 is 2, 2 modulo 2 is 0. So the first parity bit that you will get for this is 0. The second parity bit, you multiply the code word with the second column of the P matrix. So 1 into 1, so 1 into 1 is 1, 0 into 1 is 0, 1 into 0 is 0. So there's only 1, 1. So 1 modulo 2 is 1. So we get that as 1. And for the multiplication of the message with the third column of the P matrix is 1 into 0 is 0. That's 1 into 0 is 0. 0 into 1 is 0. And 1 into 1 is 1. So it's 0 plus 1 is 1. And 1 modulo 2 is 1. So that's your code word, right? So that is how you will generate your code word. And similarly, produce the H matrix, the parity check matrix, which we call as the H matrix for the decoding part, parity check matrix H. Okay, how do we make the H matrix? We take the P matrix as it is and write it. So 1 1 0 0 1 1 1 0 1. So that's the P matrix which is written as it is. And below the P matrix, you just have to put a 3 by 3 identity matrix, which is 1 0 0 0 1 0 and 0 0 1. So that is now the H matrix for the 6-3 linear code. It's not a Hamming code. Again, I'm repeating this. 6-3 is not a Hamming code. Okay, but you have seen the procedure how we create the generator matrix and how we create the parity check matrix. Again, take the code word that you have received and multiply the code word with the parity matrix, and if it is all zeros, you will see that you decide that it is having no errors, and if having some syndrome, then it has error. Okay? That procedure is 6-3 linear code. You've seen today the generator matrix for the 6-3 code, as well as the parity check matrix for the 6-3 code. Again, the important points that you need to remember is the rows of the parity matrix cannot be all zeros. If you see these 3 rows here, none of them is all zeros. Second point, there is no repetition of any row. The values are not repeated. Every row is different. And the third point is all the rows have at least 2 ones. So there is no row which has less than 2 ones. Okay, so the first row has 2 ones, the second row has 2 ones, the third row also has 2 ones. Okay, I'll leave it as an exercise for you to calculate all the 8 code words and compare the Hamming distance between all possible combinations and find out what is the minimum Hamming distance for the 6-3 linear code. Okay, and when we say linear, what does it mean? It means that when we add any 2 code words, it will give another code word from the same set. So we have a set of 8 code words. Say for example, you add code word number 1 and code word number 2. It will give the answer which is from those 8 code words. It will be one of those 8. Okay, these are called as linear. If this property is satisfied, the coding technique or the code is called as a linear code. Okay, right. So that brings us to the end of linear codes. You have seen 2 types. One is the Hamming code, which is the more important type, and then we've also seen the linear code for 6-3. Okay, like this, you can create linear codes for any code rate. In this case, for the 6-3 code, the code rate is half, or the coding efficiency is 50%. Okay, now I'm going to introduce you to a different idea about codes and representing the code vectors. Okay, so you see these code vectors, they are represented as vectors of ones and zeros. You see, it's a vector containing numbers which are either 1 or 0. Now today I will introduce you to another way of representing this. It's called as the polynomial representation of the code words, or polynomial representation of binary sequences. Okay, I will take you through that today. What do we mean by the polynomial representation? So I'm going to erase the board again. So please take a screenshot of the board quickly in the next 5 seconds. The polynomial representation is a very straightforward, very simple thing, which you are all familiar with. Okay, we are just going to apply that in a different way for error detection and error correction, how to produce codes. It is something which you are all familiar with. You've studied this from your high school probably. So we're just going to use those ideas and represent these code vectors. Okay, we'll represent the code vectors as polynomials. All right, guys, I'm going to erase the board now. So we call this as the polynomial representation of binary sequences. Okay, I will take one very simple example of binary sequences of length 2. For example, if I have a binary sequence of length 2, what are the different combinations we can have? With length 2, we can have 0, 0, 0, 1, 1, 0, 1, 1. Okay, if you want to represent this as a polynomial, basically it's like, in this case, the polynomial is 0. In this case, the polynomial is 1. In this case, the polynomial, we'll call it as d. And in this case, it is d plus 1. How did we get this? The rightmost bit is d power 0. Then the one to the left of it is d power 1. And then you go to the left of it, if you have more, d power 2, d power 3, and so on, right? So it is like how you write your for example, you have x squared plus x plus 1, right? The constant factor is x power 0, x power 1, x power 2, right? Similarly, instead of x, for the coding technique, we are going to use the variable d here, okay? So if the position is a 1, that power element will be present. If it is 0, it is not present. For example, in the first one, d power 1 is 0. So 0 times d power 1 is 0 plus 0 times 1 is 0. The second one has the d power 0 term and the d power 1 term is 0. So d power 0 is basically anything power 0 is 1. So you get the polynomial representation as 1. The third one, which is 1, 0, the third sequence, 1, 0, it is having an element, a 1 in d power 1. So d power 1 is mawjood, and d power 0 is 0 times d power 0. So there is no d power 0 here. Okay. And in this case, the last one, we have both d power 1 and d power 0. So d power 1 is d and d power 0 is 1. So you get this as d plus 1. So that is basically the way you represent a code word or a binary sequence as a polynomial. Why we are doing this, you will see in a while. We use such polynomials to create code words in a different way. Just as we created code words previously using a generator matrix, we will now create code words using some polynomials. So they are called as polynomial based codes. We will let's do some more examples of representing binary sequences as polynomials, and then we will also see how to create a particular polynomial based code. Okay, so this is for length 2. If we did it for length 3, we have 8 possible, let me call this as d power 0, d power 1, and d power 2. Because it is length 3, we will have now uh, 3 positions, so d power 0, d power 1, d power 2, and with length 3 we have 8 possible combinations starting from 0, 0, 0, 0, 0, 1, and so on, right? 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So we have 8 possible combinations here. So obviously this is all 0. So the polynomial is simply 0. This one, the polynomial is 1 because only d power 0 is present. D power 0 is 1. This is going to be simply d power 1, which is d. This is d power 1 plus d power 0, which is 1. What is this? D power 2. D power 1 term is 0. D power 0 is 0. So it's simply d square. This one will be d square plus d term is 0. D power 0 term is 1. So it's d square plus 1. This will be d power 2. So there is, for the power 2 you have a 1, plus for the power 1 is also a 1, so it's d power 1, and the d power 0 term is 0, so it is not there. And the last one would be d square plus d plus 1. Okay, so this is how we create the polynomial representation of any binary sequence. So for any length of the code word, you can represent the code as a polynomial. Okay, now the first property that you need to see here, or the first characteristic that you see here, is for a sequence of length 2, this example, right? When we had the length as 2, the polynomial is of degree 1, right? The maximum power in the polynomial is d power 1. So we say the polynomial is degree 1. That means the highest power in the polynomial is 1. So that if you see all these polynomials here, the highest power here is d power 1. Similarly, if you see for the sequence of length 3, which we have seen here, for length 3, polynomial is of degree 2, right? And in general, for any length n, the polynomial will be of degree n minus 1. So in general, for any length n, the polynomial is of degree n minus 1. Okay, so when n is 2, the degree is 1. When n is 3, the degree is 2, and so on. And that makes sense, right? Because the power 0 term will be the constant term, which will be the last term. It's basically something similar to the equations that you have studied, right? That is like x power 0, x power 1, x power 2. So similarly, it's like d power 0, d power 1, d power 2. So we are now representing the code words or binary sequences as polynomials. Why we are going to do this, why we are seeing this, is because we are going to use such polynomials to create another type of codes. Okay, and again we will concentrate on the 7-4 code, and we'll see how to create a 7-4 code using the polynomial representation. But again, what we are going to create is not a Hamming code. Okay, it is 7-4, but not a 7-4 Hamming code. The code rate is the same as a 7-4 Hamming code, but the characteristics of the code are not the same as the Hamming code. The Hamming code is different. Okay, so we will do another example of a 7-4 code, but it is not a Hamming code, and it is, in fact, you will see that it is not even a systematic code. In the systematic code, you had the first part of the generator matrix as the identity matrix. That means you had the message bits appearing as they are in the code word. But when you do it with the polynomial, you will see that the message bits are not appearing as they are in the code word. They get mixed up. So they are no longer systematic. Okay. So we will see how to do how to produce a 7-4 code using the polynomial representation. Okay. All right. I'll clear the board. Please take a screenshot of the screen before I clear the board. Okay, guys, I'm going to clear the board now. Right. The polynomial idea, excuse me, the polynomial idea is going to be used to create a type of codes called as cyclic codes. We're going to create a new type of codes called cyclic codes. First of all, what do we mean by cyclic codes, and how do we create the cyclic codes? Okay. The first property of the cyclic code is that it's a linear code. Cyclic codes are linear codes. That means if you take any two code words and add them, it will produce another code word from the same family, from the same set. Okay, so that means cyclic codes are still linear codes. And the second property is that any cyclic shift of a code word, any cyclic shift. What do we mean by the cyclic shift? I will give you an example now. Any cyclic shift of a code word produces another code word. What do we mean by that? A cyclic shift means rotating the code word. So if I take, say, let me take one particular code word. Let me explain to you first of all what do we mean by a cyclic shift. For example, if I have a binary sequence which we call as, say, 0 1 1 0, okay, a cyclic shift means rotating this either in the counterclockwise direction or in the clockwise direction, bit by bit. That means we shift the last bit and bring it to the first bit. So the last 0 comes here, the first 0 comes here, this one comes here, and this one comes here. So that's one cyclic shift in the counterclockwise direction. If I shift this again, then this one is going to come here, and the 0 is going to go here, the 0 is going to go here, and this one is going to come here. So that's another cyclic shift. So you see, a cyclic shift means make the last bit value as the first bit value, the first as the second bit value, the second as the third, and the third as the fourth, right? So you shift the bits in a cycle. It's like putting it on a circle and rotating them. Like, I don't know if you've seen these locks with the numbers, right? You have locks which you can use for your suitcase, which have a password like the numbers. You rotate those numbers, right? So it's like rotating them, and it rotates in a circle. So one cyclic shift, so one position cyclic shift will change all the positions by one element, right? So similarly, we have shifted this 2 times now, shifted one more time, so that means this will come here, this will go here. So the first becomes second, the second becomes the third, and the third becomes the fourth. So you have 1 1 0 0. Do it one more time and see what you get. So this 0 will now come here, that's 0, and this one comes here, this one comes here, and this 0 comes here. So after how many shifts we have got back the same code word? We started with 110 and we have ended up with 0110. So each time a cyclic shift is done, we get something else. Another cyclic shift, we get something else. Another cyclic shift, we get something else. So that's the first shift, that's the second shift, the third shift, and on the fourth shift. Because we have 4 bits, after 4 shifts, it will become the same. If there are 3 bits, if the sequence is 3 bits long, then after 3 shifts, it will become the same. If it is n bits, after n shifts, it will become the same, right? So for 4 bits, after 4 shifts, we got back the same code word. But if after shifting it, the result that you get, for example, we shifted the original value and we got this 0011. If 110 is a code word and 0011 is also a code word, then these two are belonging to the cyclic code word or the cyclic code. They belong to a family of cyclic codes. Again, when 0011 is shifted, you get 1001. If that 1001 is also a code word in that set, then all these three belong to the cyclic codes family, right? So a cyclic code is one in which a cyclic shift of any code word produces another code word from the same set of codes, right? So we have seen the example here where we did the shift to the right. We have shifted the bits to the right. We can do the same thing. I'll start with the same example, 0, 1, 1, 0, but we'll now shift it to the left and go in this direction. Okay, so that means we are shifting the bits one by one to the left, but the leftmost bit will go out and come as the rightmost bit. So this will go down here, 0. This will come inside here. This will come inside here. And this will come here. So we get 1100. Again, shift it one more time. That means the leftmost bit will go out and come here. The rightmost bit will come in one position, so that's 0. Then this comes in one position, that's 0. And this comes here, so that's 1. So we have now a cyclic shift in the clockwise direction. That is, it is shifted to the left. Okay, in the example here, we have seen the shift to the right. Now we are seeing the shift to the left. Let's do it one more time. So this will come here as 1. This comes here as 1. This comes here as 0. And this becomes 0. Okay, and one more, you should get back the original sequence that you started with. So this will come here as 0. This 1 will come here. This 1 will come here. And this 0 comes here. Okay, so after 4 shifts, you see again, we have got back the same answer, right? So a cyclic shift produces another code word. If that is the case, then we will all those such coding scheme or the coding technique is a cyclic coding technique, and the codes that are produced, they are called as cyclic codes. So the cyclic code has the property that a cyclic shift produces another valid code word. Now, excuse me. All right, guys, take a screenshot of the screen before I erase it, and then I will introduce you to some of the ideas behind creating such code words. Right, let's erase the board now. To generate the cyclic code, we use what is called as generator polynomial. Generator polynomial of 4 cyclic code. Okay, now the first thing that we need to understand about the generator polynomial is, because it's an NK code, NK, N in this case is 7 and K in this case is 4. That means the messages have 4 bits each. So we write messages as polynomials, it will be of degree 3. If the length of the messages of the bit sequence is 4, then the degree of the polynomial is 3, right? So message polynomial, message polynomial must be represented as a polynomial with 4 bits. For the message have 16 different messages, so therefore we are going to have 16 different polynomials, and all these polynomials will have high degree of 4 minus 1, or nothing will be then 4 minus 1. The power of the polynomial, the d power thing, the value it can have is d power 3, that is d power 4 minus 1. So message polynomials are of degree 4 minus 1, which is k minus 1, which is 3. Well, I don't know how to erase this that has come up, because if I erase it, the entire screen will go. So I'll just leave it as it is now. And then the next we need to understand the generator polynomial. We are going to add, for 4 bits of message, we are going to add 3 parity bits. So for 3 parity bits, we need to have a generator polynomial. So the generator polynomial will have, that is a property that we're talking about. Okay, we are not representing the parity bits as a polynomial, but we are talking about the generator polynomial, which multiplied with the message polynomial will create the code word. Okay, so the generator polynomial will have degree n minus k. In this case, n minus k is 7 minus 4. That is 7 minus 4, which is equal to 3. So the generator polynomial is also going to be of degree 3. And once you create the code word polynomial is of degree n minus 1, which is in this case 7 minus 1. So the code word polynomial, the highest value that it will have is power 6, right? Why d power 6? Because the code word is going to be of length 7. The C could be of length 7. So it was from 0 to on the rightmost, and it will end at d power 6 on the leftmost bit, right? So the code polynomial will be, what happened? Hello? Where is screen gone? Guys, are you able to see my screen? No. See it? Are you able to see the screen now? Hello, can you guys still hear me? Blank. Okay, you can see the blank screen, right? Okay, no problem. Okay, let me write it all over again. Okay. Oh, astaghfirullah. You can hear me and you can see my screen also, right? So I'll have to rewrite those points. Okay. Generator polynomial for 7-4 cyclic code. Okay, I'm just going to write some properties of it and I will continue in the next lecture. So the first point is the message is of 4 bits long. So the message polynomial is of degree k minus 1, which is in this case 4 minus 1, which is 3. And then the generator polynomial the generator polynomial will be is going to be having a degree n minus k, degree n minus k, which is in this case 7 minus 4, which is 3. And the code word polynomial, once you create the code words, the code word polynomial will be having a degree of n minus 1, which is in this case 7 minus 1, which is 6. Okay, now how do we produce the code word? So we will take the message polynomial, which we will call as I of d, the information bits, right? So the information bits, which are 4 bits long, we'll represent that as a polynomial, and we'll call that as the message polynomial or the information polynomial. We'll call it as I of d, and we will multiply the information polynomial with the generator polynomial, which we will call as g of d, and that will give us the code word polynomial, which we will call as c of d. Okay, now I'm just going to give you one condition of g of d. Because we are going to create a code word of block length 7, that is n, right? So the generator polynomial g of d is a factor. How do you choose it, right? Is a factor of d power n plus 1. In this case, n is 7. So we'll take a polynomial d power 7 plus 1, and we have to factorize this. So of 16, for example, if I give you a number 16, 2 is a factor of 16, 4 is a factor of 16, right? 4 into 4 is 16, right? So we have to have some other polynomial which exactly divides this d power 7 plus 1 without any remainder. So that will give us the generator polynomial, and it must be of power n minus k. That means it must be a factor of d power n plus 1, and it should have a degree of n minus k. That means in this case it should be a factor of d power 7 plus 1, and it should have a degree of d power 3, right? So we will see that in the next lecture. We will factorize this d power 7 plus 1 and use the generator polynomial to create the code word, and then also we will see how to create the other polynomial, which is called as the parity check polynomial, to do the decoding process at the receiver side. Okay, I will stop here for today, and we will continue again from here in the next lecture. And I will now allow you to ask any questions that you might have. So send your questions either as your chat, or just turn on your microphone and start speaking. Okay, if you have any questions, please ask me now, and we can have a discussion very quickly before we wind up for today. And while you are thinking about your questions, let me also announce to you, I think some of you are facing problems with the Blackboard quizzes. You said you don't have enough time, blah, blah, blah. Guys, you need to remember that a quiz on Blackboard is a test, and a test means you need to prepare before the test. Okay, if you prepare before the test, the time for the test will be more than sufficient for you. Those who are complaining that you don't have enough time to complete the test, it means that you did not study for the test. You are sitting for the test and then trying to search for answers in the notes during the test. If you are going to sit and search for answers from the notes and from the text during the test, you are not going to have enough time to complete the test. A test means you prepare for the test before the test and then start the test. Okay, even for the next quiz which I have announced, I think for next Saturday or Sunday, prepare for the test and start the test. Inshallah, you will be fine. If you don't prepare, what can I do? Right? Even if I give you 10 days time, it will not be sufficient if you don't prepare for the test. Okay, if you do an exam in the classroom, for example, you did your mid-1 exam, you are given 1 hour, and that 1 hour means you have to study before the question and then you have to come. If you don't study and come and you say I will search where is the answer in the book, that means you will spend half the time looking for the answers. That's not going to be enough for you. Okay, I have given you 5 questions or 10 questions. It's all multiple choice questions, and when you're doing multiple choice questions, if you have already read the notes, you should do each question in less than 30 seconds, but I give you double the time, more than double the time. For 10 questions you get 12 minutes and something like this, right? In the last quiz I gave you 8 questions for 12 minutes. If you have studied, you should have no problem. If you are having problems, it only means that you are not preparing before the test. If you don't prepare, there is nothing your teacher can do for you. What if it closed in the first minute? Well, that's a different problem. If you have internet connection problems, if you have internet connection problems, if you have problems with the Blackboard, that's a different matter. Okay, but I'm talking about those who have no issues with the connection but still complain that you don't have time to finish the test, right? It only means that you have not studied properly for the test. Okay, yes, Suleiman, is quantization error equal to bit error? No, quantization error is different from bit error. Quantization error comes from the process of quantization, where, for example, you have a sample of value 1.1 and you made it as 1 volt. So there is a difference between the original sample and the quantized sample of 0.1 in this case, right? So that 0.1 is the error. Okay, quantization error is different from bit error. Quantization error occurs in the A to D process, where, again, let me give you an example. If you sample a signal at a particular time, and if that sample value is, say, 1.15, and the quantization is done so that 1.15 is made as 1 volt, 1.15 volt is made as 1 volt, that means there is an error of 0.15 in the quantized value. So this is quantization error. A bit error is different. When you transmit the bits, suppose you transmit a 1, you get a 0, or you transmit a 0, you get a 1. The bit has changed its value. A 1 became a 0, or a 0 became a 1. This is called as the bit error. Okay, how to calculate the bit error? You need to compare the bits that were transmitted and that were received. For example, if I transmitted 000 and if you get 111, that means there are 3 errors in that. So the bit error is calculated in terms of the total bits transmitted and the total errors out of them. For example, if I transmit 100 bits, out of the 100 bits, 5 bits are error. That means the error probability is 5 by 100. 5 out of the 100 are Harban. Yani 5 errors out of 100 bits that I transmitted. So if I transmit 1 million bits, in 1 million, one bit is error. That means 1 out of 1 million, yani 10 power minus 6. 1 by 10 power 6 is 10 power minus 6. Okay. Those who have a lecture, please move on. And those who have any questions, you can stay on and ask me your questions. So the bit error is calculated in terms of how many bits were transmitted and how many were error. So out of 1 million, if one bit is error, we call it as 1 out of 1 million, yani 10 power minus 6. And in practical applications, that is what we have. We have error probability 10 power minus 6, 10 power minus 10, 10 power minus 15, and so on. Okay, so we need to have very low error probability. That is called as the bit error. Is that clear, Suleiman? Right. So quantization error is different from bit error. Okay. All right, guys. Those who have lectures to continue, move on to your next lecture, and I will close this session for now. And we will meet again in the next lecture. And prepare well for your next quiz, which is on Saturday. And also the assignment that I gave you, just write it by yourself. Okay, you don't need to worry. Just write it on your own. Just don't copy from your friends. Write it from the notes. Write it from the textbook. You will be perfectly fine.